What specific problem does your method aim to solve regarding the stability of transformer model activations, and how does it contribute to understanding robustness in these models?
Our method aims to solve the problem of understanding the stability of transformer model activations by identifying and analyzing stable regions within the residual stream after the first layer. We specifically investigate how small perturbations in activations affect model outputs, revealing that these stable regions can lead to minimal changes in output when within the same region, but significant changes at the boundaries. By interpolating between different prompts, we demonstrate that semantically similar prompts tend to occupy the same stable region, while dissimilar prompts occupy distinct regions, which contributes to our understanding of the model's robustness. Our findings indicate that as training progresses and model size increases, these stable regions become more defined, suggesting that the model's robustness is linked to the emergence and refinement of these regions. This work enhances our comprehension of how transformers maintain stability in their predictions despite variations in input, which is crucial for their reliability in practical applications.
Can you explain step by step how your proposed method, particularly the activation patching technique, works? Please include details on any mathematical formulations or functional mappings involved.
The proposed method utilizes an activation patching technique to analyze the stability of the residual stream activations in transformers. Specifically for a given prompt, P, we define a function, f_p, math_bb_r_d right arrow math_bb_r_d, that returns the residual stream activations after the last layer at the last sequence position. The activation patching involves replacing the activations after the first layer with a modified version, represented as A plus alpha BA, where A and B are the activations corresponding to prompts P_A and P_B, respectively, and alpha is an interpolation coefficient ranging from 0 to 1. The distance between the outputs of the clean run-on, P_A, and the patched run is measured using the L_2 norm, expressed mathematically as d alpha equals f_P_A f_P_A A plus alpha BA_2. This formulation allows us to assess how small changes in activations affect the model's output, revealing the presence of stable regions and their boundaries based on the rate of change in d alpha.
Could you provide a specific example illustrating the inner workings of your proposed algorithm using the activation interpolation between two prompts? How do the results of your example support your claims about stable regions?
In our experiments, we constructed pairs of prompts to illustrate the activation interpolation, specifically using dissimilar prompts D1 and similar prompts S1. For dissimilar prompts D1, the house at the end of the street was very, and the house at the end of the street was in. We observed a nonlinear change in the model output as we interpolated between their activations. This resulted in a flat region at the beginning and end of the interpolation, with a sharp jump in the output, indicating that these prompts occupy distinct stable regions. In contrast, for similar prompts S1, she opened the dusty book and a cloud of mist, and she opened the dusty book and a cloud of dust. The output change was linear throughout the interpolation, suggesting that these prompts belong to the same stable region. This difference in behavior supports our claim that semantically similar prompts are more likely to reside within the same stable region, while dissimilar prompts are separated by distinct boundaries.
What theoretical or practical benefits does your method provide compared to previous works, particularly regarding understanding and measuring the properties of stable regions in transformer activations?
Our method offers significant theoretical and practical benefits over previous works by providing a clearer understanding of stable regions within transformer activations. Unlike prior studies that focused on smaller polytopes, our findings indicate that stable regions are much larger and correspond to semantic distinctions, allowing for a more nuanced analysis of model behavior. We demonstrate that small changes in activations within these stable regions lead to minimal output changes, while crossing region boundaries results in significant output differences, which is crucial for understanding model robustness. Additionally, our interpolation approach allows for efficient measurement of the rate of change in model outputs, revealing the emergence and refinement of these stable regions throughout training and as model size increases. This methodology not only enhances our understanding of transformer dynamics, but also provides a framework for future research into the relationship between model architecture, training progress, and activation stability.
How did you validate your method? Please elaborate on your experimental design, including the datasets used, metrics for evaluation, and any comparative analysis with baseline models.
To validate our method, we conducted experiments using models from the Quen2 and Olmo families, with parameters ranging from 0.5b to 7b. We sampled 1,000 pairs of unrelated 10-token-long prompts from the Seth Gutenberg_English dataset to analyze the interpolation between activations. The primary metric for evaluation was the L2 distance, d alpha, between model outputs as we interpolated between prompts, which allowed us to assess the stability of activations across different regions. We compared the results across varying model sizes and training progress, observing that the curves representing the relative distance became sharper with increased model size and training tokens, indicating the emergence of stable regions. Additionally, we analyzed the shapes of the distance curves for semantically similar and dissimilar prompts, confirming that similar prompts exhibited linear changes while dissimilar prompts showed nonlinear behavior, further validating our hypothesis about stable regions.
What significant results did you find in your experiments regarding stable regions in transformer activations, and how do these results change with model size and training progress?
In our experiments, we found that the residual stream of a trained transformer can be divided into stable regions, where small changes in activations lead to minimal changes in output, while significant output differences occur at region boundaries. We observed that semantically similar prompts tend to occupy the same stable region, indicated by a linear change in model output during interpolation, whereas dissimilar prompts show nonlinear changes, suggesting they occupy distinct regions. As model size increases, the boundaries between these stable regions become sharper, which we quantified by measuring the maximum slope of the relative distance between outputs. Additionally, we noted that during training, the curves representing the relationship between activations and outputs transition from linear to sharper shapes, indicating the emergence and refinement of stable regions. This sharpening effect is more pronounced in larger models and continues to evolve as training progresses, suggesting that both the development of new stable regions and the definition of existing boundaries contribute to this phenomenon.